All right, so we've looked at the basics of the probability, the foundational probability. We now want to look at distributions, how particular random variables are distributed. And there are two kinds of distributions. One is discrete, one is continuous. We want to look at the first of the discrete, and then next time we shall look at three more discretes. And then after that, we'll look at the continuous. So let's look at a particular experiment here. Suppose you have a coin, and the coin has a probability of occurring between 0 and 1 inclusive. And any of those numbers can turn up, and the coin toss will yield a head or a tail. If you toss the coin multiple times and you observe the outcome, laptop is frozen. Okay, then we can make the following assumptions about a coin. That each trial has only two outcomes, success and failure. That the probability of success, or H, which in this case is like the head, is P. And the probability of failure is 1 minus P, or Q. And that the trials are independent. In such a case, we are dealing with a Bernoulli trial, and hence a Bernoulli distribution. In a Bernoulli distribution, if you toss a coin once and the random variable X is denoted by X, and then you have successes and failures, the possibility of that 0 all the way to 1 inclusive will only have a binary outcome of 0 and 1 instead of the 0 up to 1. And whenever the random variable is 1, it means that you have had a success or you've had a head. And if it is equal to 0, it means you've had a tail or you've had a failure. When a random variable takes only two values, such a variable is known as a Bernoulli variable. In fact, in usual econometrics, which we shall do next semester, it is sometimes simply called limited dependent or binary, just as we did in management science, and we looked at binary. So the binomial distribution becomes a Bernoulli distribution in this case. Now, if the probability that X is equal to 1, or that is X is happening, is P, then the probability that X is not happening is Q, which is 1 minus P. Yeah, Emily, I'm not recording, right?
Yeah. Doc, please, you are recording.
Okay.
Yes. Please, can you go over the difference between the binomial and then the binomial distribution? I'm not very clear on that. What makes them different?
Between the binomial,
yes,
and the binomial distribution.
The Bernoulli, no, the one.
Oh, Bernoulli.
Yes.
Bernoulli and binomial. Bernoulli is when you're looking at one option. Okay, when you have only one outcome. But then the binomial is when you have multiple trials instead of one trial. Bernoulli distribution and binomial distribution. Okay, so one looks more at one trial, whereas the other looks at multiple. Or let me put it this way. The binomial distribution, you have, in fact, in both of them, you still having success and failure, isn't it?
Yes.
Have you heard of, there's a word for one of them instead of binomial. Instead of Bernoulli. There's one they call Benoni. What's Benoni that?
No, Doc.
Well, which of you have said about Benoni?
Heard of Benoli before?
Sorry?
I think I've heard about it before. The Benoli.
Word when I can't mention That's a whole
Be,
book. Ghana.
Be, Benoli. Benoli.
Yeah. So Bernoulli is more or less like part of binomial. Emily, Bernoulli is like when you are moving from class 1 to class 6 and you have only class 1.
Okay.
It is a single trial. It is a single trial and it has 2 outcomes. But then the binomial, you have a number of successes in multiple Bernoullis, okay, multiple independent trials. So you have multiple times for the binomial. So you have multiple Bernoullis. Let me just put it out. Multiple Bernoullis make binomial. Does that make sense? You can toss a coin once, isn't it? You can toss a coin once, can't you?
Yes. Yes.
And the outcomes are what?
Either success or failure, depending on which one you
So the
want.
outcomes are 0 or 1.
Yes.
And the trials are how many?
1.
Yes. But you can also toss the coin 3 times or 4 times. And in each case, the outcomes are how many?
Look, in each case, the outcome is 1. Either you succeed or you fail.
Yeah, it's binomial. That's what we mean.
Okay.
The outcome is binomial. I mean, when you say 1, it's a little bit confusing. But the outcomes are either 0 or 1.
Okay.
But then how many times did you do the trial? It is 3 times or 4 times. And therefore, you have moved away from Bernoulli to binomial. So binomial is more or less like the plural of Bernoulli. But that depends on the number of trials. If it is in a form of a coin toss, it's the number of times you threw the coin. Does that make sense?
Yes, Doc. Thank you.
But that's the main difference. Now, the probability function of any random variable for a Bernoulli trial or binomial is given as this, okay? Where you have the probability of occurrence and the probability of the non-occurrence. Okay. So sometimes when you want to say that a particular random variable X is binomially distributed, this is how you write it, okay? It's binomially distributed with the probability of small p. This probability of small p is a probability of success. The probability of success is a small p, whereas the probability of failure is the kill, which is 1 minus p. And we know that expected value is the probability of success. The mean of that particular random variable is p. Okay, and then the variance of that random variable, when you look at this, because remember that the variance is the mean square. The mean square. So it's the expected value of the mean square. Okay, the expected value of the mean square. And so when you want to find the variance, it's just the p square. And you have p square. Actually, this is not how it's supposed to be. Okay, it's 1 minus. It's 1 minus. It's p and 1 minus p. That's how it is. It's p and 1 minus p, which would then give you pq, which is the variance. But we've done this before, okay, where we indicated that the variance is pq, and then, but this is only for Bernoulli trial. Let me put that clear. This is for only Bernoulli trial. It's not for binomial, because if it is for binomial, we are going to have NP, and we'll come back to that. But this is for Bernoulli trial. In a Bernoulli trial, because the trials are ones, okay, the number of n that you are dealing with is only one. And so you wouldn't have multiple n. Okay. When we take binomial, you will get a picture. So let's go to binomial. That will make a better sense. The probability of success is P. The probability of success is P. Please, this capital P and this small p are the same. The probability of success, because we are using the coin as the main example, the probability of the head is the probability of success. So technically, the P of H is the same as the P of S, which is the same as the small p. Okay. Which is the same as the small p. By the way, I'm using a different laptop. Let me increase the weight of this thing. Yeah, this is better. Okay. So I've indicated that the probability of failure is Q, which is the 1 minus the P. Okay. And in a binomial trial, you repeat the experiment multiple times. Okay. So the number of trials are many. And then you can now find any aspect of the distribution you want to find. You can find the mean, you can find the variance, you can find the standard deviation. So let's look at them one by one. So in a binomial distribution, we say X is binomially distributed with a sample of N and the probability of success of P. The expected value, which is the mean, is the sample size multiplied by the P. Then the variance is that expected value multiplied by the probability of failure. Okay. And because the Bernoulli trial, I told you that N is 1. Okay. That is why, if you could remember, it ended up becoming PQ, okay, for the variance. But here, N is not 1 in a binomial, and so it will end up with NPQ. And then, of course, the standard deviation is the square root of the variance in that case. Does that make sense? Any question? Any question before we proceed with an example? Yes, go ahead.
Please, the expected value, is it, are we talking about the outcome of the probability?
We are talking about the average of the outcome of the probability.
Oh, okay.
The average of the outcome. But remember, the outcomes are either head or tail, right?
Yes, please.
Yeah, the average of that.
Yes,
it doesn't
please.
make sense to take the average of that, but it is the average of that.
Yes.
But that it depends on the number of times, isn't it?
Yes.
That's why you see that the average is being multiplied by n.
Yes. Thank you.
So if I'm going to the hospital and I'm expecting a man or a woman to take care of me, the probability of, okay, so let's say that I'm a man, and so I'm going to check a certain part of my body I don't want a woman to see. So I'm expecting a man. That is my probability of success. So if I'm expecting a man, the probability of success, P, is my man appearing in the consulting room. And so at any time, because I'm expecting that, that becomes the mean, because that is my expected value. You guys understand? So if I go to the hospital with the same issue, I'm expecting a man. Then subsequent time I go there, I'm expecting a man. So that is what I'm looking for. That is my probability of success, and that is why if it is Bernoulli, then that is P. But if it is binomial, then that, of course, is going to be the number of times I go there, multiplied by the Bernoulli that I wanted. All right. So we are going to look at a typical example of a binomial question and then see the best way to address it. First thing you want to notice is that always try and identify whether the question you have is truly binomial. And if it is binomial, what makes it binomial in your eyes? What makes this question binomial? That's what you always want to ask yourself. Okay. So suppose that 20% of all 15 copies of a statistics book, they fail a certain binding strength test. So we check the strength of the book and then they fail 20% of the time. What is the probability that at most 8 fail the test? What's the probability that at least 8 fail the test? You are supposed to, first of all, identify whether this is binomial, hypergeometric, Poisson, negative binomial, or normal, or Weibull, or anything. In this very example, what gives you the clue that this is binomial? What signals binomial structure of this, Emily?
Doc, the outcomes are 2.
How do you know?
Either they pass or they fail.
Very good.
And also the n is more than 1 because 20% of 15 is more than 1.
Yeah. So the sample size is not just 1, but it's more than 1. Okay.
Yes,
So
so
the
it's
first
binomial.
one is that you have a binary choice, a fail or a pass. Of course, there are so many things that are binomially distributed. Any of you can give me an example? Give me a possible example of binomial distributed item or random variable. Jerry.
Lord, please, tossing a die, rolling a die.
No, that is not. That is not. That is not binomial. That is rather what?
That is Benoni.
No. That's what. That is not binomial. What is that? Albert. Are you with us, Albert? Albert. Emily, that is what?
No, I think is it normal distribution? I'm not too sure. Is that normal or Poisson?
No. So that is multinomial.
Okay.
There's still a cap, isn't it?
Yes.
Yes.
There's still a cap. Remember, normal distribution, is not capped. Poisson? No, Poisson deals with the average. So this is ideally would have been binomial if the caps are just 2. But this is multinomial because it's 0 to 6. Or it's 1 to 6. A die, is it 1? There's no 0, right? Or there's 0?
No,
there's
it's
no
1
0.
to
Yeah,
6.
it's 1 to 6.
1 to 6. So that's multinomial. Okay, so what makes this binomial is that you've got a binary choice here, and then a percentage of the sample size is more than 1. Take note, a percentage of the sample size is more than 1. Okay. How do you solve this? Well, you need a formula to be able to guide you. And the formula for finding the probability that a particular random variable is happening is given by these elements. There is a deep formula and there is this general one. So this particular formula, I would want you to write it because we are going to be using it quite often today. We're going to be using it multiple times today. For those that I teach the statistics, okay, the formula is slightly different. Do you remember how we used to write the formula, Emily? We normally bring factorial in the formula. Or you guys don't attend my...
Not by the NK, N up K is written, if you are expanding it, will be written as a factorial, as a combination, and that will bring in the factorial.
Yeah, of course. That's what I'm saying, that how will you write it? How will you write it? How does it look like?
It's going to be N combination K, which is the same as N factorial over N minus K factorial.
Very good. Very good. So, Ben, did you understand what he said? Is Ben really with us? Somebody should just remind him. Emily, you understood what he said?
No, so my internet just went off, so I just came back.
So you get
just heard
actually
the
n
final thing there you
factorial,
said.
n minus x, all factorial. Then you have your p raised to the power x. I'm just changing the k to x, but it's the same thing. Okay. And then you have q, or 1 minus p raised to the power n minus x. That's the formula. That is actually the probability that x is equal to a particular number, a particular small x, which is what I'm using. You can write that formula too.
Okay.
Because that is the formula you will use. Ideally, that n over, that n with the k in the bracket, that is how it is actually. Okay. So now that you've documented this formally, let's now go to the first part. Now, you have to identify the elements in this question. So in this case, let's identify the element. What's the first element to identify? What's the first element? Ben Susan, what's the first element? There are 4 elements actually. Per A. Or I should do the first one. Should I do the first one?
So the first element is the number of copies. So
that is n. N is equal to what? N is equal to what? Jeffrey.
It's going to be 20 over.
No, I say n is equal to what?
N is equals to 20%, 20 over 100 times 15.
No. Emily, what is n?
Oh, N equals 15, sorry.
Exactly. Pay attention.
Yes, please.
What is the next variable? P. What is P here?
P is, so if P is our success, then
P is not our success. P is not our success. P is a probability of success.
okay.
So what is P?
So that'll be 1 minus the fail.
What is P? P cannot be 1 minus fail.
Is it 7?
P is actually the probability of success. So what is P?
The P will be, probability of success will be 12 over 15.
No. The probability of success is just this. 20%.
Okay.
The probability of success is 0.2. Why? Because the probability of success is the probability that you are going to get a fail statistics textbook. You see, maybe you are a bit confused about the word fail. You think that the fail here cannot be success, but it should rather be failure. But remember, the failure is I could have said that defective. A statistic textbook that is defective. So the defective here is what you're looking for. So the defective is bad, but that's your probability of success, because that's what you're looking for. Suppose I go to a place and I know that they are going to attack me. I know that they are going to attack me. If they attack me, that becomes my probability of what?
The success.
Exactly. So the success is what you're expecting and experiencing it, or encountering what you're expecting. So the fact that they've attacked me, that does not make that probability of failure. No, because attack is negative. So the probability of success is the expectational, outcome. And that is 0.2, which means that our probability of failure or kill or 1 minus P is what?
0.8.
0.8.
Okay, you got that now. Then, so these are 3 things. I said there are 4 things you need. The 4th one is the X variable. And the X variable is usually from the question, not from the preamble. So from the question, what are we looking for? We are looking for the probability that at most 8 fail the test, the strength test. So that means that our X is what?
8.
But then we have to take into consideration the symbol,
Yes.
the interval symbol. So how will you write that? You will say X what? 8.
Less than equals to 8.
Very good.
Yeah.
So that is an example of this here. So it's going to be that the probability that, so first of all, X is 8, of course, but then you are now looking for the probability that X is less than or equal to 8. That's what you're looking for. And what does that actually mean? It means you are finding what? You are finding what? All the way to 8. Okay, so what it means is that you're going to find the probability that X is equal to 0, which is going to be, I mean, we know the formula already. The formula is that factorial thing that we wrote. And then you will add it to the probability that X is equal to 1. You will add it to the probability that S is equal to 2 all the way, and then you add it to the probability that S is equal to 8. 8. So once you have found all of these probabilities, what do?
You add them.
You add them. So it means that you got to find the probability that X is equal to 0 all the way to 8. 9 different probabilities, and then you sum them. If ordinarily you're using the probability table, then you will use a cumulative probability table for binomial. But this one, you have to calculate. So how do you go about it? Well, we just take the first one, okay? So we are going to find, this indicates that we are looking at the entire cumulative probability, okay? But we don't know the X variable yet. So we have to find the X variable when it is 0. Then we change it, because remember, S is from 0 all the way to 8. So you have to do X variable equal to 0, equal to 2, all the way to 8. So,
Doc,
yeah.
please, so the lower band, the summation, the lower band should be X, right? Instead of Y.
Oh, yeah. I made a typo. It's true. It's true. So this value is supposed to be X. Okay. S equal to 0 all the way to 8. Okay. So thank you. I'll change that. Next one. So you have to calculate all of this. So we are going to do for S is equal to 0. So we do for S is equal to 0. You take your 15 factorial divided by, remember, n minus 1. Okay. And then the n is 15. Okay, sorry. You have x factorial. Did I write the thing wrongly? Okay. N factorial. Yeah, I think
the
I read the
previous
thing
one
wrong.
didn't have the X factorial.
Yeah. So please check. It's x factorial into bracket n minus x all factorial. So you have to now take the n, find the 15 factorial, which is 15 times 14 times 15 times 13 times 12 times 11, all the way up to 1. And then you find the x factorial. In this case, x is 0, so 0 factorial will be 1. Then you have 15 factorial again here. So if I take this one, I can cancel these two. Okay, and the whole thing here will be what? 1. So I'm now left with this. 0.2 raised to the power 0 is what?
It's 1.
1. So you have 1 here. So now you are left with 0.8 raised to the power 15. Okay, so you take your calculator, do 0.8 to the power 15, and that will give you this number for 0 factorial. And that is the same thing we have here. Then you have to do another one for 1 factorial. Then you do another one for 2 factorial, all the way up to 8. Sorry, another one for probability that x is equal to 0, 1, 2, all the way up to 8. And once you're done for each one, you sum them up. That will give you approximately 0.9968. So what I'm going to now ask you for the subsequent ones is how are you going to work each one? If you understand this. Any question on this before I ask you that? It's going to be rotating like that. It's going to be rotating. Be writing this formula down, please. Please write it again. Down. This one. Write it again down. Okay. So let's go to the next part of that question. It says that what is the probability that 8 fail the test? What's the probability that 8 fail the test? In fact, this one, I will need an answer. Let me go to Ben Susan. What is the probability that 8 fail the test?
That's x is equal to 8.
X is equal to 8. You mean the probability that x is equal to 8?
It's equal to 8, yes.
I didn't hear the probability that.
So, sorry, the probability that x is equal to 8.
Okay, and what will be your answer?
It will be the same 0.9968.
That will not be correct. Jerry.
Done.
What to be your answer?
So, by then we would have calculated s equals 8 before getting this summation. So we will pick that answer.
What is that?
S equals 8 would have been calculated from the first one.
What is that?
Please, I have to calculate it. So we are going to have
Calculate it.
15,
Emily, what is that?
we are going to have 15.
It's going to be 0.0029.
You see, Emily is thinking and she's looking at here. That's why I showed you the screen. We have already calculated that thing.
Yes.
You said it yourself, Jerry.
Yes, please.
And now you are going to calculate. You said we have already calculated. Now you are going to calculate it. So that's it, 0.0029. That is a probability that 8 of them have failed. 8 have failed. Okay. So next one. What is the probability that at most 8 failed? Emily.
Doc, 1 minus the total answer we got from the last one. The first one.
Why?
Okay, so we know. Doc, no, the A and C are the same. So it's the 0.99 that we had.
Oh, yeah. How can it be the same like that? I mean, that's interesting. It's actually at least, it's not at most.
Okay.
Yeah. When we go to this thing, I should tell us the correct one. Let me just go down. So that's it. At least 8.
Okay, so at least 8 will be 1 minus at most 8.
Good. Okay. Ben, do you understand?
Yes, Doc, I did.
Okay. We already know at most 8. This is at most 8, which we have found to be 0.996. So 1 minus that will give you this at least. Okay. Next one. Between 4 and 7. How will you work that, Jeffrey? Between 4 and 7.
We have probability of 4 from the earlier calculation, a probability of 5, 6, and 7. You add them up.
Very good. Excellent. So you take those that you've already done, and then you add all of them up. This is what you're saying. Do 4, 5, 6, and 7. You add them up, and that'll give you 34.54%. Abbott.
No, so if you say between, does that mean it's inclusive of the 4 and 7?
Yes, when it doesn't mention that it's exclusive, then it is inclusive.
Okay. Then it's inclusive. Okay.
Yeah. The next one is the mean and the variance. The mean and the variance. Now, the mean of a binomial distribution is the sample size times P. And the variance is that answer multiplied by 1 minus P. So who can do the substitution and tell me the expected value? Emily.
Okay, Doctor, P was, N was 15, and then the P was 0.2. So the answer is 3.
Good. And the variance?
Okay, so the variance is
3 times.
3 times 0.8, which is 2.4.
Okay, perfect. So as you can see, that is exactly what you have here. So I'm giving you some of them. As we keep going, I'll be giving you a test too. Or today you thought there was not going to be a test. Albert, I think you are now used to the test, aren't you?
Yes, but
You do some proofs, don't worry. But at least you are
Please,
following what we are doing, aren't you?
yes, you are following.
yes,
But
Doctor, we are
if
following.
today can be a warm-up, so that
But that's why it's becoming a warm-up. That's why we are working together. Okay. Now, let's get the main point of a binomial exercise. So once you've gotten the successes, okay, you can always find the failures. Now, that principle is a very important principle, that once you can find the successes, you can always find the failures. Okay. Why is that important? And normally what you do is that you choose the case slots. In the case of a head and a tail, when the heads go, you choose the case slot. So we have to make a choice of how many Ks from the sample size. And that is why we have that NK in the formula that you saw. So you saw that formula for a particular reason. So we can now define a binomial random variable. A discrete random variable X is said to have a binomial distribution with parameters N and P, abbreviated to be X is binomially distributed with an N sample size and a P probability of success if it takes values that are integers. Okay. And if it takes values that are integers. And so the actual value of the random variable is what we are talking about. A discrete random variable is what we have here. It actually dances between 0 and the sample size. Of course, it can never go beyond the sample size because it is from the sample size that you are making a binomial assumption. Okay. We know that if you toss a coin n times and the probability of success is P and failure is Q or 1 minus P. If the trials are independent, then we can let X here denote the number of successes in the n trials. As you can see there. We know this already. Okay. So we can redefine, in fact, not redefinition, it's actually a repetition and a definition of the binomial probability distribution, provided that we are identifying the head as well as the tail. But for binomial to happen, all of the following must exist. Again, we know this. N trials, probability of success, independent trials, and so forth. Let's take another example. Should I make this one a test, or we should go through the example first? The thing is that you're going to get a test. There are 6 of them. You're going to get 2 of them as tests. So you got to make a decision as to, how we are going. Otherwise, if you don't choose your own first, you will now get one that are
we'll do this as a test.
Can you beg for assignment rather?
No. We are doing a test. I told you that every time we meet here, we'll be doing one test. Our manga. We do one test. I'll use this test as a justification that because assignment you can copy. Or you won't copy.
No, we don't.
Will you copy or you won't copy?
No, we promise we will not copy.
In fact, that alone itself means you'll copy.
Hey, Doc.
My mind was that if you should say that, Doc, we are human beings, will copy, then I know that you wouldn't have copied. But the fact that you say you will not copy is the clear reason why you copy.
Oh,
no.
And I don't mean you are copying from your friend. You copy from ChatGPT. You copy from somewhere. That's what I mean.
No. When we get an assignment, we discuss.
You discuss.
That's even more copying than copying.
That is improve our understanding.
That understanding improvement itself is a copying process. It's plagiarism. You guys are. Okay. Suppose you're a tennis player and you make successful first serve. Okay. 70.
But please, we'll do this as the test, please. Because the more we go forward, the more difficult it will be.
I'm telling you, the last one, they don't want to go there.
So we'll do this.
There are 6.
Guys, let's do this one.
Yes.
Okay. The last one, I can show you. So that you know that you can't even go there. So it's better that you are doing them. You are going to do 2. So out of the 6, you're going to do 2. So if you want to do this, no problem. I'll give you the next. Let me see how easy or difficult it is. Oh, it's simple. It's simple. I'll give you 10 minutes. Get it rolling. 10 minutes. And remember, you do it on your paper. You do it on your paper. Write it all properly on your paper. Some of them might require a sentence or 2. And then when you're done, you take the picture and send me. So the first trial is a Bernoulli trial, which means the probability of the good serve was 70%. This was in the question. Then we are told that the sample size is 80. So X will become the number of the good serves within the 80 trials. That's what it means. Okay. So first question is, what is the mean and the standard deviation? Well, you know the formula for the mean and the formula for the standard deviation. So if we distribute it like this, the mean is going to be 80 times 70%, which will give you 56. Ben Susan, Albert, you got that? You got what? Rather 24. So instead of using 70%, you rather use 30%. Why will you do that?
No, Doc, I used the mean I did 80 times 70%. I got 56.
Okay, that's the first picture. Okay, yes. Then,
yes,
Emily, you got 56 as well, so that's fine there. And then the last minute, even yours, I can't even see. Oh, you multiplied all of them. So you had 80%, or you had 56 as well. Okay, so you both got that. That is actually the 1 mark. Then the standard deviation, because the question says that find the standard deviation. And as you know, the standard deviation is just the square root of the variance NPQ. And that means you have 56 times 3. That is times 0.3. and that will give you 4.1. 4.1. Jerry, you had that. And Emily, you had that. And Albert. Albert. You had that as well. Okay, so that is 2.5 in general. The next part is verify that we can use normal distribution to do this. Now, how do you verify? It's very simple, very simple. So the rule for the normal distribution condition is that the mean should be greater or equal to 10, and then the n times the Q should also be greater or equal to 10. Okay. So when you take the mean, 56 is greater than 10, you just say that 56 is greater than 10, and then the NQ is also 24, which is greater than 10. And so we can approximate the whole thing, which was normally distributed with the 80 N and 70% P. We can now say that it can be normally distributed with 56, which is the mean, as well as 4.10 being the standard deviation, because normal distribution is defined by the mean and the standard deviation. So, Albert, what did you say? You say that we can fit the normal made since both are greater than that. Yes, what I needed here is the ability to write the normal distribution. Indicate that because the mean is this and then the standard deviation is that. Because normal distribution requires that. And so you have 4 over 10. Sorry, 4 over 5. Albert. Let me see Emily as well. Emily, you said it is greater than that. This is greater. Both conditions are satisfied. Okay, but you also did not put it in a normally distributed mean and standard deviation. So you also had 4 over 5. Let's go to Jerry. Jerry, you use the mean. What did you write?
But please, for mine, can you check the B part again? I wrote for normal model, and then I wrote the distribution where the mean is equal to this and the standard is equal to this.
Yeah. I think you did that initially, not in the end.
Yes.
Yeah. Oh, perfect. That's exactly what I want.
Okay.
That's exactly what I want. You wrote it. You even indicated the mean and the standard deviation. So that's 5.5. Albert, should I also go back and check yours?
No, please don't. I didn't miss it anyway.
Now, Jerry, I don't see top of what you've done at all. You have found the usual variance as we know, but you didn't write the conditions. And you didn't finish.
Yes, look.
Yeah, you didn't finish. So for that second part, you are going to get 1.5. 1.5. So you have 4. Yeah, no. 1.5 plus 2.5. No, you can't have 4. You have 3.5, and I'm taking out your 1.
Oh, no,
so you have
no.
2.5.
No,
I'll round your 2.5. Around your 2.5 to 3.
Yes, please.
Okay, so
thank you so much.
we have 3, 4, 5. Okay. Take note of that.
Thank you, Doc.
So this is it. At least you understand what you've done. Imagine this is an actual exam test. There's nothing you can do. And you guys are actually going to write exam tests for your final exams. So it's important that you are understanding all of this, because all of them will come from some of these. So for example, I can say that under what circumstances can this be Poisson distributed? What is the normal approximation to Poisson distribution? So always think outside the box. Okay, let's go to the next one. Okay. The question is whether you want this one or we should continue. Suppose that 20% of all copies of a particular textbook fail a binding certain strength. Let X denote the number of blah, 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 blah. Find, I think we've done this already. If you guys could remember, we've done this already. This is where you will compile all of them. Binomially distributed with the sample size and the probability of success. You compute that is between 4 and 7. So you compute for 4, for 5, for 6, for 7, add them together, and that is going to give you 34.77%. So this one is good. Now, we've got question what? 4. We've got question 4, 5, 6. And like I said before, you wouldn't want to look at 6. So you now have between question 4 and question 5. Question for you. What would you want to look at as your test? Is it 4 or question 5? The thing is that you don't see question 5, isn't it? You don't see question 5. You see question 4. So you have to have a forecast probability mindset to know whether you're going to do the 4 or the 6 or the 5. And like I said, the 6 didn't go there. So what do you want to do? Class rep, decide for your family. Are you there?
Sorry, yes, Doc.
Since you have decided that you're going to do this, I'm going to give you another, this time 15 minutes to execute this policy here. A company that produces fine crystals from experience, that 10% of its goblets have cosmetic flaws and must be classified as seconds. Among 6 randomly selected goblets, how likely is it that only one is a second? Among 6 randomly selected goblets, what is the probability that at least 2 are seconds? And if goblets are examined one by one, what is the probability that at most 5 must be selected to find 4 that are not seconds? That last one is cacophony. I wish you all the very best. In 15 minutes, we'll regroup and see how your brain has helped you.
Doc, please.
Yeah, I just realized that I even needed to stop the recording, pause the recording. You want what? Explanation about the C?
Yes.
So the C says, if goblets are examined one by one, what is the probability that at most 5? So now you know the probability of at most 5. It is 5 or more.
Yes.
But then
Yes.
you have also been told that out of the at most 5, your goal is to find 4 that are not seconds. Now remember that all along A and B, you are looking for those that are seconds. That is those that are faulty. Remember that in the top part here, you were told that
Yes.
goblets have cosmetic flaws. And that's
Yes.
why they are classified as seconds. So those that are defective, mistaken, flaws, faulty, they are the ones that are seconds. Now, the first question was asking you about those that are seconds. The second is asking, now look at the first one. If the first is asking you, find me one that is a second, and you have been told that there are 6, then if I had asked you, find me one that is not a second, it will be the other 5, isn't it?
Yes.
Does it make sense?
Yes, Doc.
Now, the B part says that among that same 6, what is the probability that at least 2 are seconds? So 2 are seconds here means that now you are not looking at, it says at least. So you are not looking at, you're looking at what to what?
2 to 6.
Okay. Which means that I could have also asked you what is the probability that at least 2 are not
At
seconds.
most 2 is not. Yeah.
No, even at least 2 are not seconds. If I had said at least 2 are not seconds, that is at most 2 are seconds. Or let me put it up. That is at most. No, that is not at most. That is less than 2 are seconds.
Yes.
You get a point, because you are just taking 1 minus whatever you have there to find the not seconds. Okay, so with that principle in mind, you come to the third one. He's told you that at most 5. Okay, now from that at most 5, he says that find 4 that are not seconds. Now you could easily find at most 5. Okay, but
Yes.
then at most 5, that means that you have all the way from where to 5.
You have from 1 to 5.
Yeah, but find the probability that 4, okay, out of that 5, you got to select it in order to find 4 that are not seconds. So what are the 4 that are not seconds there? Remember, if you're going to find at most 5 that are seconds, at most 5 that are seconds is from 0 to 5. Now we are looking for 4 that are not seconds among that.
Okay, so that's the probability of failure in this case.
Because but if you have gotten 0 to 5, okay, remember you are actually picking it from below going above, isn't it?
Yes.
At most means you are from below going above, and the highest point is what? 5.
Yes.
And so now if I tell you that, if I say that find me those that are not seconds in all of this, what would that be? It will be none of them.
Yes.
It will be 0. Because from that 0 to 5, all of them are seconds. So if I tell you that find me, those that are not seconds, it will be all of them. If I tell you that find me 1, that is not a second, you're going to give me what? You're going to give me 1. But if I should tell you that find me, because remember the at most is still capturing it. The at most is, so if I tell you that find me 2 that are not seconds, the 2 that are not seconds are 0, 1, and 2. Oh, sorry, 0, 1. Because remember,
0, 1.
Do you understand? 2 that are not seconds is 0, 1.
Yes, Doc.
And I'm talking about that are not seconds from the 5. So it means that no, the 2 that are not seconds are 0, 1, which means that those that are, sorry, the 2 that are seconds, if I say that give me 2 that are seconds from this, it will be 0, 1, 2. But if I say that give me 2 that are not seconds, I'm being careful with my choice of it. If I say give me 2 that are not seconds, it will be 2, 3, 4, 5. In other words, it is from the below going to the above. Because remember, the whole thing was from at most. So the at most, you come from the below. Okay. You come from the below going to the 5. So if I say that give me 5 that are not seconds, it's going to be 5. Give me 2 that are not seconds, it's going to be 2, 3, 4, 5. Give me 1 that are not seconds, it's going to be 1, 2, 3, 4, 5. If I say give me 3 that are not seconds, it's going to be 3, 4, 5. Because you've captured already the at most part. So if I say that give me 3 that are not seconds, first of all, you got to know where you are picking them from. Because those that are seconds are normally from below going to that number. So if I tell you give me 3 that are not seconds, it has to be from that 3 upwards. I've done enough explanation. You should be able to think with this. The rest of you, are you listening?
Doc, so if you know the highest threshold, like that most, you just pick it and ensure that you don't get to that number.
You pick it and rather ensure that you hit that number. Because remember, you start from 0 to that number.
Okay.
You start from 0 to that number. So whatever you pick, okay, that especially when you're dealing with not seconds, whatever you pick ends at that number.
Oh, okay.
From the number in question ends at that number. And then you calculate the probability of all of that and then sum them. Bro, if I tell you that 70% are men and 30% are women, okay, and I ask you what is the probability that, and there are 15 people, you know, and I said 70% are men. You have to calculate 70%, but I can ask you a question on those that are women. So you have to go and take the opposite to be able to give it to me. I'm giving you 3 minutes and then that's it. You don't have to get everything.
Hey, not the 15 minutes are up.
Oh, you've spent 20 minutes. You started 11:19. So we are now in 19 minutes. Let's start the show working. I want to believe that the first one, all of you got it. Okay. We have 6, so we'll work it this way. Probability that X is equal to 1. The question was only 1. So only 1 is just 35.43. Jerry had that. Albert had that. And then Emily had that. Okay, so that's cool. The second one is a probability of 2. Says among 6, at least 2. At least 2 means that you do 2 to 6 or you do 0, 1, 2. You do 2 to 6 or 0, 1. Okay, 0, 1. Okay. So just do 0, 1 like this and subtract it from 1. And that should give you approximately 11.43. Emily had that. Jerry, you are still sending.
No, I'm done.
11.43. Jerry too had that. One thing I like about Jerry is that he does what he can and then he leaves the rest for God, isn't it?
Yes, Doc.
I've seen that a lot about you. Like you don't stress like Jerry will be doing, and then he will delay time. Yeah, that thing they fail already. You know. Okay, so you all have that thing so far. So this is the key one. So this not means that since it was 4, you're supposed to calculate for 4 and 5 goblets. That's all. You know, that is all. And then so you calculate for the 4 and 5 goblet. Now, the 4 goblet with a 0 effect is when the probability of S equals to 0. The 4 goblets, one of which has a defect or second, and then the 5th is a good one. So you calculate when it is 4, okay, it's 1, and then the 5th is a good one. And then you will now take the 2, and then you will sum them together. So the probability of 4 seconds is 4. Is 4. Let me go to the question again. Okay. At most 5 must be selected to find 4 that are not seconds. Okay. But watch it. It says that if goblets are examined one by one, one by one, one by one. Okay. So if I'm examining them one by one, I will have to examine them from 0 to what number? To 5. You agree with that?
Yes, Doc.
Yes,
Good.
that is
So if I'm examining them from 0 to 5, the probability that we are selecting 4 goblets that don't have defects, 4 out of the 5 that don't have defects will be what?
No, that's the one where none of it, so it will be the probability of it being equal to 0.
Exactly. And then the probability that we are selecting 4 goblets, 1 has a defect. But of course, the 5th one is good. And the reason why the 5th one is good is because of the utmost. If 1 has got a defect, okay, remember, if 1 has got a defect, then it means that your chances of getting out all of the 5 selected, the chances of getting 1 out of the defect, if 4 is selected, is going to be 1. And so you calculate the probability of the 0, you calculate the probability of the 1, and then you sum the 2 of them. So you sum the 65 and the 26%, and that gives you 91.85%. Let me see. I know Jerry didn't get there. And I also know that Emily, you got the first one, right? I didn't get a second one. Oh, you finished?
No.
Yeah, you got a second.
No, Doc.
Yeah. So you got a first one, you didn't get a second one. So that last one alone is 2 marks. The first two is, and that's how it is. The difficult one is the one that has the 2 marks. So the first two is 1.5 marks each. All of you have got that, 3. The last one, all of you got 0 except Emily, who had 1 for calculating the first one. Okay. So that gives you a mark of 334. Take note of that.
Okay, Doc.
Okay. Now, if I should open the 5th question, you would have wished you have done that. I'm sorry. I'm sorry.
Okay, Doc, we'll do it again.
No, man, you need to do it again.
The choices were made. The choices were made. Okay. And it is a very, very cool, collected question. Now, 20% of all telephones of a certain type are submitted for service while under warranty. 20%. Out of these, 60% can be repaired, whereas the other 40% must be replaced with new units. If a company buys 10 of these telephones, what is the probability that exactly 2 will end up being replaced under warranty? How do you go about it? Okay, so we have those that will be submitted and those that will be replaced, isn't it? So we can say that we have to identify some key percentage values. We need to first of all find the probability that a phone will be submitted, the probability that a phone will be replaced. So let's say that this is a probability that a phone is going to be replaced. That's a probability that a phone is going to be replaced. But now the R here is actually signifying the R alone is signifying replacement of the phone. So you are submitting the phone for service and because it needs to be replaced. So the P of R is the probability that the phone is going to be replaced. But watch it very carefully. The probability that the phone is going to be replaced is going to be the probability that a phone is submitted times the conditional probability that it's replaced. Look at why. It says that of these, what is that of these? What is that of these? The 20%.
Yes, the previous sentence.
The 20% of the telephones, that are submitted for service. Okay. So out of that 20%, 60% can be repaired, 40 replaced. 40 replaced. So if I actually want to know those that will be replaced, I need to know those that have been submitted first. Do you agree with that?
No.
I need
Yes.
to know those that are
No.
submitted first. Now, which means that the probability of being replaced is conditioned on the probability of being submitted. Do you agree with that?
Yes, no.
Yes.
You agree with that? Very good. Now we need to
Yes,
find
please.
the probability of being submitted. What is probability of being submitted? What is that?
0.2.
It's 20%.
0.2.
Very good.
Yeah.
Now, what is the probability of being replaced given that it's been submitted?
0.6.
So the probability of being replaced given that it's been submitted is 0.6. You all get it so far? Oh, no, it's not 0.6.
Okay, Doc, 40. Okay.
40, exactly.
Sorry, it's 0.4. Yeah.
And listen.
Okay, so Doc, then which one represents the 60? The repaired.
Which one? Exactly, that's the one we are going to do. Okay, so the repaired or replace, okay, I'm not going to write it here. The probability of being repaired or replaced is the probability of being submitted multiplied by the probability of being repaired given that it's been submitted. Take a note and watch.
That will be 0.08.
It will be 0.08 as long as you understand what I've written. So it will be 0.2 multiplied by 0.4, giving 0. It's not 0.8, it's 0.08.
Yes, 0.08.
So you have the probability of being repaired. Now watch this. Now you select a company. You select a company. You buy. If a company buys 10 of these telephones, what is the probability that exactly 2 will be replaced? Now you understand this. If we say that, let me just, because now we have a binomial situation here, because we have been given a 10. Okay, so the number among the 10 phones that must be replaced here already has a binomial condition. Why? Because you say that if a company buys 10, what is the probability that exactly 2 will end up being replaced? Now, being replaced or not being replaced itself makes it what? A binomial situation.
Yes.
Does that make sense? So we are going to
Yes, please.
We are going to use binomial situation, but the question is, are we going to use x greater than 2, equal to 2, less than 2, or greater or equal to 2, or less or equal to 2, or what? Which one?
What is it? Exactly.
That it will be, yeah, exactly 2, so equal to 2.
Equals to 2.
Exactly.
So probability of x equals 2.
That is exactly what you're going to find. And that is what you're going to use to find. But you need to identify what is now going to be your P, because now that you know it's binomial, in binomial, there are 3 things that you need. The first one is your N. N is what?
Like n is 10.
N is 10. Now you also need your P. P is what?
Look, from here you can see P is 0.08.
Exactly.
The replace, because that's
exactly. So P is 0.08.
No, but the confusing thing is then which one is the 60%, the repaired?
Now, the 60% is what can be repaired.
So it's different from replaced. Exactly.
It's different from replaced. It's different from replaced. Okay. That 60% is actually a split between the replaced and the repaired. Because remember, both of them were given different probabilities.
Yes.
But then the focus now is on the what? The replaced.
Okay.
Good. So you have 0.08, which means that your Q is what?
0.02.
92.
Yeah, 0.92. Okay, so you substitute that into the binomial formula. So you're going to get n factorial, which is 10 factorial, divided by x factorial, which is 2 factorial, into bracket 10 minus 2 factorial, which is 8 factorial. Okay, and then the rest will be 0.08 to the power x, which is 2, and then 0.92 to the power n minus x, which is 8. And then you calculate, and then you can find your, having an understanding is what is key here. So the question is that if you had gotten this, would you have been able to do that? This is it.
Jerry,
Yeah.
I think the first one
would
you
you
did was
still
better.
have wanted this? Doc, we are glad we chose the first one.
Yeah, I think
It
so.
wouldn't have come
that
to
one was
mind.
better.
Yeah.
It wouldn't have come to mind to use the
Yes,
conditional probability here.
Yes.
Yeah. And so that is why, you know, God told Abraham, listen to your wife. Mhm. Like the one you had, what was the mark? The mark was what?
5.
No, this one, how did I distribute it? Was
Doc,
it 334 or 223?
No, Doc, 433.
This last one.
Yes, 433.
Hey, this one carries. Hey.
So that is what I did. Like, if you don't take it, you don't even get one. As for Albert, he will make life easier for himself. Okay, we go to the last thing for today. The last one, you see, I'm putting it all, even though you're learning, it's all in the form of a question as well. So we have an X random variable, which is binomially distributed with a sample size and a probability of success, as we know. If n is fixed, are there values of the probability between 0 and 1 inclusive, whereby the expected value of x equals 0? If they are, or if they are not, explain. Remember, I told you that this one is not a small boy. Are there values? Are there values? Now, the first thing you got to do is to find the expected value of x. What is it?
I think the expected value is the NP.
Yes. So this is n times p. Okay. We know that by principle. But the question is not asking you to find the question is asking you, if you look at it, it says that if n is fixed, unmovable, are there values where that number is equal to 0, where this is equal to 0? That's the question. Are there values where that is equal to 0? Under what condition are there values? Under what conditions are there no values? So the first thing you got to understand is that looking at the interval he gave you, is p equals to 0 allowed or is not allowed?
It's allowed.
It's allowed. Good.
Oh.
It's allowed. So p can be 0. So when p is 0, what does that mean in terms of each trial? It means that each trial has a 0 probability of happening, right? Isn't it?
Yes.
Yeah.
Yes.
It means that the probability of success, because that is p is equal to, the probability of success is 0, which means that that particular random variable is what? It's itself 0.
Yeah.
Because for you to have a probability of, occurrence being 0, then it means you're not there in the first place. The x itself is equal to 0 for that to happen. For you to have the probability of p equals to 0, then the probability of 1, let me put it this way, not probability of 1, okay, it means that x must be equal to 1 for p to be equal to 0. Sorry, x must be equal to 0 for p to be equal to 0. I wanted to process that before. So the question of whether or not, it says that, are there values of t for which this is 0? Yes, there are. There are values of p for which the expected value of x is equal to 0. And that is when x is equal to 0. Okay. When p is equal to 0, okay, it means that each trial has a 0 probability of success, which implies that x is going to be 0. But x is going to be 0 with a probability of 1. X is going to be 0 with the probability of 1. In other words, the random variable being 0 has a 1 probability of happening. For you to have a probability of 0, okay, for p to have a probability of 0, it means that x itself is 0. It's not there. The random variable is absent with when p is equal to 0. And when p is equal to 0, you multiply 0 by n. It doesn't matter whether n is fixed or, once you multiply 0 by n, that is 0 times n, and therefore the expected value of the random variable will be equal to 0. So that's the first one. Let me show you how you should document it. Okay. So this is the explanation that will make sense. That's why I'm saying that this one will require you to do some write-up. It requires some bit of understanding, a bit of knowledge expansion before. It's not just calculation, but knowledge expansion to be able to get it. What was the second one? The second one says that for what values of p is the variance maximized? Now, the word maximize is the same as optimize. Do you agree with that?
Yes.
Okay. Anytime you are trying to find any normal equation and you want to find whether it's maximized, you take the first derivative. Do you agree with that?
Yes.
And then normally you set it to 0, you find the value, and then you take the second derivative to check whether it's minimized, it's maximized.
Yes.
Okay. So now, for what value of p? In other words, tell me the value of the p, the probability, when the variance of the x is maximized. Now that means that the first thing you got to write down is what? You can tell me. The first thing you got to...
Doc, the formula for the variance.
Excellent. That's the first thing. Now, let's document the formula for the variance. Variance of x. What is it? We should know because we
Doc,
already
is
have.
n. Yeah, np is into brackets 1 minus p.
Very good. So this is the variance of x. Now, watch it very carefully. Watch it very, very, very carefully. This function can be expanded. Do you agree with that?
Yes.
Okay, let's expand it. But I'm going to use a small letter here. Okay. Let me just use a small letter. It is a variance of what do I want to say? A v of p. Okay, and then let's expand it now. What will be the expansion? The first will be np minus np squared.
np squared.
Okay, now watch it very carefully. If I were to rearrange it, it becomes a quadratic function. Do you know that?
Yes.
Yes.
So technically, it's like having minus np squared plus np, and then if there's a number, you can add a number, say k or c or something, constant, isn't it? So we are in a world of quadratic. Now, for such a quadratic function, every quadratic function, we must, there's a formula for calculating quadratic function. What I mean is that you can have something like, a p squared You forget about that. I'm replacing it so that you see a proper quadratic function. You can have AP square plus BP, okay? And then you can have minus
C
and plus, isn't it?
plus C.
Plus C, exactly. So this is a quadratic function. And you know there's a quadratic formula that you can use to find this value.
Yes.
A, B, and C are all numbers. Okay, but let's look for a situation. If you want to know whether it's maximized, what do? You take the first derivative. And then you can find the highest value, because the highest value is the vertex, isn't it? The highest value. Oh, by the way, do you know that quadratic function looks like a parabola? Like this.
Yes.
You know that? So the maximized point is what? The question says maximize. The maximum point is the vertex, the upper part. Yeah. So if you want to find that highest point, what will be the value of P? What will be the value of P? Okay. Well, one thing you can do is I can differentiate it with respect to what P. Just as if it was X, we would have done. We differentiate it with respect to P. What would that be? If you differentiate this function, let's call the function, I call the function VP. So let me say I differentiate this VP. I differentiate this VP with respect to P.
It will be 2AP plus B.
2AP
plus B.
plus B. You all agree? And then you set it equal to what?
0.
Good.
0.
So you are setting it equal to 0 and finding the value of P. So set it equal to 0, find the value of P. Okay. One of them should be minus. I think I missed it. Remember this one here means there was a minus here, isn't it?
Yes, yes.
Okay.
So I need to bring the minus here. Yes. Okay, so now we move this one to this side. You actually switch. So you can actually have 2AP
plus B
equal to B. Sorry, minus 2AP equals to B. So it means that P will be equal to what?
But then it will be negative B.
Yes, the negative will
Oh, sorry.
If P goes to the other side.
Yes. Oh, wait. Oh.
The negatives will cancel out.
No, wait.
So you shall have
the negatives will cancel out. Did you say the negatives will cancel out?
yes, because it will be negative 2AP equals negative B. So that
No.
will
I made a mistake. I made a mistake by bringing the negatives here, please. I made a mistake. So this negatives here, because what I'm doing is I'm just taking, you see, I've not brought this function here. Let me show you. I have not actually brought this. I just created this function that you're seeing here. The usual function for finding a quadratic function. I created a quadratic function here using the probability P, and then I decided to differentiate it. So I'm not supposed to bring this one here. I just have to leave it as it is. Okay. But then this will be minus, isn't it? Do you agree with that? Check it.
Yes.
In that case,
Good.
yes.
So that will be minus.
It will be.
Because
Yeah.
I've moved it to this side. So if I want P, I differentiate both sides by 2A, isn't it?
2A. Yes.
So you get minus B over
E over 2A.
2A. Now we will bring our values. Our values we had in the original function here. Let me use a different color. We'll bring our values. Where's that? This one. Yeah. We bring that values because at this stage, we know that what was the value of A? If you look at this one, the value of A is standing for what in our equation? A is a minus n. Do you see that?
Yes.
A stands for minus n.
Yes, Doc.
Okay.
Good. So this A here that you are seeing here is minus n. Okay. So P is equal to minus B. B stands for what?
And
B is now
N.
our N.
N. Exactly.
N.
Okay. B is our n. So we are going to have minus n for the B divided by 2A. And A itself is what? Minus n.
minus n.
Minus
So
N.
that's going to be minus 2n. And this is actually equal to what? When you check it.
Doc, what about 2?
Wow.
Half. Exactly. So this is half. Okay. So what does this mean? Okay. This means that at this point, that is when the variance is maximized. So this means that the variance is maximized at this very point. But this is the first derivative we took, and then we set it to 0 and then find the original p-value, which is what? Half. As to whether this half is truly what is going to maximize, we normally would take the second derivative. That's what we normally do. Okay, but you put this one down. So I'm going to clean this, and then we take the second derivative. So how will you take the second derivative of the first derivative? Because we've already concluded that when P is equal to half, that is when the variance of x is maximum. But you can't just leave it there. You got to prove the second derivative. How do you do that? Well, let me rewrite our equation again. The variance of the P is given by this, okay, equals to NP1 minus P. You all remember this?
Yes.
Yes, Doc.
Yes.
Okay. And then we've been able to take the first derivative. And when we took the first derivative, we were able to come with a conclusion that P is equal to half. Do you remember that?
Yes, Doc.
Yes.
Okay. Now we are going to take the second derivative of the first derivative. But remember, before we set it to equal to 0, what was it? Before we set it to 0,
we're trying to look at
when we
whether it is
created the
maximum
first
or minimum.
derivative, do you remember what it was?
Doc, I think it was N.
There's
It was
2n.
N minus 2NP.
Yeah, getting there. N minus
2NP.
2NP.
Yes.
Chief of Staff, do you remember? I'm talking about Papa Jerry.
Yes, please, Doc, I remember.
But do you know that this can also be rewritten as N into bracket 1 minus 2P?
2p. Yes, please.
You get
Yes,
that?
Doc.
So
Yes.
this is our first derivative. Now we are going to do the second derivation of this first derivation. So you have to do D
Squared
2 vein, because our distance was vein up there. So it's going to be D2 vein divided by dP squared.
Yes.
You remember second derivatives, right?
Yes, Doc.
Yeah. D2 vein divided by dP squared. And when you do that for this very example, what do you get? For this very example,
Doc, you get minus 2N.
exactly, you get minus 2N. And is this negative?
Yes.
Yes.
And normally, if this is negative, if this is 0, what does that mean? It means that,
maximum.
exactly, it means that the original one is at maximum. So if this is
Yes.
negative, it means that the P equals to half. That actually maximizes the variance, is truly at the maximum point. So we can now say that since this is negative, because n, we know n is not going to be negative, n is going to be positive. Okay, so the whole thing, minus 2n is going to be negative. Then it means that we have been able to maximize the parabola. And therefore, the variance attains the maximum at p equals to half.
Okay.
Albert, you would have been able to solve this, right?
Doc,
So this is
please,
the first one. Okay. And this is the second one that we just did. Okay. You take the function, you calculate for the upper bound, and then you substitute these values that we have. We had p to be this, which we come back to the first derivative. This is what we actually had. And now you take the second derivative of that first derivative. Okay. This second derivative will yield minus 2n, which is actually at the maximum because n is positive. And then you have the variance attaining the maximum value of that. That's it. That is how you have been able to prove what value of p maximizes the parabola and whether it is really at the maximum. Any number can be given to you for you to prove, whether it is at maximum. Any function, you can be able to prove whether it's at maximum. How do you do that? You can take the first derivative, set it equal to 0, get the number. Okay. Then you take the second derivative, and then simplify it, and that second derivative must be negative. And once it is, it means the first one, that gives you the number, is at maximum. That brings us to the end of the entire caboodle. Next time we'll look at hypergeometric distribution, negative binomial distribution, Poisson distribution. These three. We'll look at them. Any question?